we're going to have a very interesting lecture today. First thing first. So, Thursday, we discussed curvature. So we said that the basic problem that we want to solve is how does the presence of energy or mass curves space-time. For that, we first need to know what we mean space-time is a curve. Define curve space-time. And we did a few things. The first thing we had to do is the power of transport, define it properly. What does it mean of parallel transporting the vector? Namely, transporting a vector parallel to itself. So parallel to itself is very simple. We say that the parallel derivative along the path that we take is 0. So v over lambda, and I said that sometimes in textbook you'll find it over d lambda. It's written like that. Not you want mu. Just dx sigma over lambda, blah blah sigma v nu. Which we divide d v nu over lambda plus gamma nu sigma rho dx sigma over lambda v rho. And we generalize that part of the transported energy. Then we look at what do we mean by curvature. How do we know that the space-time is curved? That led us to define tensor, which we call the Riemann tensor. We said, okay, let's say that we have a point, which I call it 0, 0. I have a vector here. And I parallel transport this vector to a different point, yielding two different paths. The passes are defined, so this would be 0, 0. And the passes are defined by two vectors, a mu and b nu. It's an infinitesimal path. This will be delta a 0, this will be 0, delta b, and this will be delta a, delta b. We said that one way of telling whether the space-time is curved or flat is simply to take this vector, parallel transport it along this path back to the point and see whether we got the same result or not. We chose a slightly different method. We just looked at parallel transporting the vector twice, from 0, 0 to delta A, delta B. And then taking the commutator differences. Found out that delta B vector delta B rho is just delta A, delta B, A mu, B nu, and then that's R, rho sigma mu nu, B sigma. And R rho sigma mu nu is that Riemann tensor. It's a 1-3 tensor. Tensor, which we call Riemann tensor. And then we actually carry this calculation to derive this tensor, and we find it is equal to R rho sigma mu. D mu gamma rho mu sigma minus D mu gamma rho mu sigma plus gamma rho mu, then index lambda mu sigma minus gamma rho mu gamma index lambda, gamma, lambda, and mu. This is how this tensor is defined. So there is something which looks quite conspiracy here, because we said gammas, Aristotle symbols or defined connections, they are not tensors. But somehow we take, multiply both of them, then we take the derivative, we add them in a certain way, and we end up with something which is. This is a very complicated tensor. That's one thing. Basically, once we know the metric, it's straightforward to derive this tensor. Opposite is not true. But straightforward to derive this tensor is, requires some calculation. It's not that straightforward. You need to take the metric, inverse metric, the derivative of the metric. That's just to get gamma. Then we need to take the derivative of that, multiply that. So it's definitely something which is not trivial at all. But bottom line is that the metric gives us all the information we need to know about to calculate the Riemann tensor. Then we said the Riemann tensor has several important consequences. The first most important is that a theorem that says that the necessary theorem, which I only partially proved to you, that is that a necessary and sufficient condition for the metric to be equivalent to the Gaussian metric. Is that R is that one all components of curvature tensor everywhere to that metric mu has three positive one negative eigenvalues. So this is a necessary and sufficient condition. We now have a foolproof way of knowing whether a metric is flat or not. I don't think you had it in your homework, right? And sometimes you see a metric, which is Euclidean metric, which is written in curvilinear coordinates of whatever kind. So it's not obvious necessarily that the metric that you're seeing is flat or not. Now you know how to do it. You simply have to calculate the curvature tensor, which you can always do once you have a metric. If it's all zeros, then you know the condition is fulfilled and the metric is flat. Yes?
In most physical problems, can we always diagonalize the metric?
Well, in all physical problems that we encounter here, yes.
Yeah,
and again, we're not talking about we're not talking about string theories of n-dimensional, etc. We're talking about general relativity, and the answer is always yes. Or let's say I have not encountered in my scientific life any metric that was unable to that.
Symmetric. It's symmetric.
Yeah, but practically yes. I mean, thing is, I mean, we discussed that. I mean, metric is almost Riemann. You could envision various theories of various metrics which are not, but this is more for either mathematicians. I mean, if you go and study mathematics and differential topology, really, differential physics, I'm not an expert in string theories, so possibly it appears there. I don't know any other place in physics where you see this sort of crazy metrics or something. So you don't really need to worry about it. It's more, think of it, know it exists, know where it comes from. If whenever sometimes in the future life you come to that, you know where it is coming from, and what it really is. That's right. No question. Okay. So, you know, you don't need to worry about that. The only thing I want you is to know that this thing exists. Okay?
Because in the last homework, there was a question about inverse metric, how we can throw a false just replies elements of the metric. It's inverse. So, I mean, in general, it's not true, but I mean,
if you have
in
a
most
metric,
physical cases, it's true, right?
yeah, well, if you have the only way you cannot diagonalize the metric is if it has a zero eigenvalue.
Yes.
But it doesn't happen in any of our physical scenarios that we encounter. Okay, so that should be quite clear. Don't try, you know. I'm a physicist. I'm not a mathematician, right? So if this was a mathematics department, I could say, okay, I mean, you can think of some examples or some crazy examples. In the physics world that I'm living in, that I'm familiar with, it doesn't happen. Can it happen? You know, in the mathematical world, possibly yes. In real world, I'm not familiar with. Okay, that solves the problem. So this is the theory which is quite important. And then we spend some time deriving algebraic properties of the Riemann tensor. So we said in principle, in n dimensions, there should be n to the 4 components, independent components of the Riemann tensor, which is a huge number. In reality, there are less, because the Riemann tensor obeys some symmetric properties. So we did some algebra, which was a bit ugly. But I don't get too much excited by that. First, because I already know. I definitely told you, go and do that. I'm not excited because I actually did. I spent a few hours just to make sure that I'm doing all these things properly and not mixing any indexes. So definitely do it at least once in your life. That's important for you. But then at the end of the day, this is algebra. There's nothing more than that. Just making sure that you're not mixing indexes. So it's a good exercise to make sure that you get yourself familiar with how to do this, not to get too much confused with all these Greek indexes that are here. But at the end of the day, we end up with three properties of the curvature tensor. The curvature tensor is symmetric under interchange of the first pair of indices and the second pair. So you end up with R, rho, R, rho, sigma, mu, R, mu, rho, sigma. And we said this is anti-symmetric in exchange of any of the two indices. So R, rho, sigma, mu is minus R, sigma, rho. Minus R rho sigma mu is an R sigma rho mu. And we have the cyclicity in the last three indices. R rho sigma mu plus R rho. Just take the second sum here. So mu sigma plus R rho mu sigma mu is equal to 0. Now we did two more important things over here. So one, we defined the Ricci tensor by making a fraction. So we had Ricci tensor R mu R lambda mu and the Ricci scalar. This is symmetric. R mu is mu. And the which is scalar R, which we define as R mu, which is G R mu. And then for the properties, then we found out that in n dimensions, we end up that the total number of independent components the Riemann tensor are 12 squared minus 1. Give you for examples. Obviously, when we talk about 2 dimensions, that we only give a one independent component. We talk about one-dimensional space, there are no independent components. One-dimensional space cannot be considered to be curved or flat. It's almost flat, basically. 4 dimensions, which is of interest, well, there should be 12. Right? What? 16 times 15 divided by 12. 3 times 5. This is 4 by 4. 3 times 5. 15 divided by 12. This is 4, 3, 5. N dimensions. All right. Questions? I already don't like it so fast. Something quite is going to happen. I think there's something quite, some quite nice things you need to have to do. No? No means everything is clear. I asked you about that in the exam. You know perfect how to answer. That's the meaning of no questions.
Well, if let's say in 2 dimensions, you can calculate the Riemann tensor, and one find the component is 0, it's meaning it's a flat space.
No.
How
So
come
in order to get, no, there will be zeros. There will be components which are 0.
Okay.
But there will be one independent component, meaning that there could be one component which is non-zero, and others will be dependent on it. Right? In order to set the space-time flat, it's not enough to compute one. But you need to calculate all of them. All components of the curvature vanish everywhere. Okay? I'm going to give you an example.
But in 2D space, there's only one independent.
Which means that all the others, non-zero, would be dependent on it,
And
because of this symmetry. But if I tell you that R 1, 2, 3, 4 is equal to some number, then you know automatically that 1, 3, 4, 1, 2 will be equal to the same number.
oh, okay, but if it's one independent is 0, doesn't
The
mean
one
that
no.
it's flat.
If all of them, get this, it has n to the 4 components. That's not going to change. The thing is that most of these components are going to be dependent on each other,
Okay.
right? Because of these relations, right? If I tell you that R 1, 2, 3, 4 is equal to some constant C, whatever, that means that R 3, 4, 2, 1, 1, 2 is equal to the same constant. And R 2, 1, 3, 4 is equal to the minus of the constant. Right?
But this equation we cannot really understand what's.
That just tells you how many independent.
Yes.
I'm going to give you an example. That means that all the components of R in 2 dimensions. But how many components we have in R in 2 dimensions?
2 to the 4.
2 to the 4, right? So 16. There'll be 16 components. There'll be 16 components of R. Doesn't mean you're going to have 16 independent numbers. There'll be 1, and the rest will be either dependent on that or be equal to 0. Okay? You'll see that if I didn't give you already, I should give you homework. No. All right, more questions? So before we give you a few examples, there was one thing I didn't do last time that we need to complete. Let's do that. So there are several properties. There is one extra property, extra identity, associated with the Riemann tensor. That's called the Bianchi identity. So you can understand there are many Italians in this business. So Bianchi identity is not an algebraic identity, but it's a differential identity. So again, it's just a mathematical identity. I'm saying just, but actually it's the most important one, differential identity, which let's say that I have the Riemann tensor, and I evaluate the value of the Riemann tensor in a locally inertial coordinate system. What happens in a locally inertial coordinate system? What happens to gamma? Yeah, right. The affine connection is 0, but the derivative of the affine connection doesn't have to be equal to 0. Right. In a locally inertial frame, gamma lambda mu is equal to 0, but its derivative is not necessarily. So we end up that nabla take the derivative of the r, nabla r or sigma mu. So this is a covariant derivative, but I can only use the regular derivative. B lambda r rho sigma mu. So this is 1/2 B lambda d mu d sigma g mu minus d mu d rho g mu sigma minus d mu d sigma g rho mu plus d mu rho g mu sigma. Just by plugging in r, is the gamma is equal to 0. Okay, just use a definition, nothing more than that. And then the Bianchi identity simply says that what happens if I take the cyclic permutation of the first 3 indexes. So what is the cyclic permutation of the first 3 indices? That means lambda r rho sigma mu plus lambda rho r sigma lambda mu plus lambda sigma r lambda rho. What? Well, it's pretty straightforward. Just plug it in. 1/2 times d lambda d mu d sigma g rho mu minus d here lambda. I'll just switch to that's okay. D lambda d mu d rho g mu sigma minus d lambda d mu d sigma g rho mu plus d lambda d mu d rho g mu sigma. That's for the first. Now for the second, plus d rho d lambda is equal nu minus d rho d nu d sigma g nu lambda minus d rho d nu lambda g sigma nu plus d rho d nu d sigma g nu lambda plus sigma d nu d rho d lambda nu minus d sigma d nu d lambda g rho minus d sigma nu rho g lambda nu plus d sigma nu d lambda g nu rho. Here. You go this one versus this one. Should be sigma. This one versus this one. Should be lambda. Versus this one. Let's go new. Versus this. No sigma. This and this, so we end up, surprise, surprise, this is 0. This is equal to 0. Now, instead we derive it in a local inertial frame where gamma is equal to 0. But this is a tensorial equation. And given a tensorial equation, if it's true in one frame, it's true in every frame. This is always true. So, tensorial equation, therefore it's true. Okay. Now, because of the anti-symmetry we have, you can write it the way is to write the Bianchi identity as lambda r rho sigma mu. When I put the square brackets, that means cyclic permutation. This is called a Bianchi. It's Bianchi, not Bianchi, it's Italian. Some pronounced names in Italian.
By saying that it's tensorial equation true in any frame, you mean in any locally inertial frame?
No, any frame. Doesn't have to be local inertia. It's nothing about the frame. Now, there's a very nice form of the Bianchi identity, which we get by having a twice contraction. So take that identity here. Just leave this one, write it again. What we do is sigma G mu lambda. I know this is equal to 0. Right, I took this equation, I tried it twice, so I get what I get here. This gives me a nabla of mu. Here I have mu sigma. Nu and sigma are contracted, so I can switch the order here, right? One's twice. This is the second and fourth. Okay, so I have G nu sigma R rho sigma mu is equal to G nu sigma R sigma rho mu, right? Which is equal to R nu rho mu is equal to what? This is the Ricci tensor. R rho mu. Here I get the same thing. So here I have a nabla rho. Here I have R, so G nu sigma G nu lambda is times R sigma lambda mu. This is the second term. So I switch those. So I have minus G nu sigma G nu lambda R sigma lambda mu. Right. So this is a minus G nu sigma R sigma mu. Right, so I have a contraction here. So again, switch it again. Sorry, switch both of them again. So this is a minus G nu sigma R and mu sigma mu. This is minus G nu sigma R sigma mu, which is a what? This is a Ricci. Which is scalar, right? So this is minus R mu. This is minus R. So I got here minus rather than plus R. And the same for the third time. You're all following me? Should be quite straightforward if you make it all the way through here. Good. Here it's the same thing, and now contracting again. Lambda rho. So lambda. Let's get it plus lambda. Excuse me, mu. Or lambda rho mu. Then I'm just raising the lambda to mu. I contract, so that's R rho. Equal to 0. Now nu and mu are the same, right? I mean this is. So we switch that. So we end up with lambda mu R rho mu is equal to 1/2 lambda rho R. It's the same Bianchi identity. Let me just define a new tensor, which I'm going to call Einstein tensor, where it tells you that we're getting close to something which is quite important. Einstein tensor, which is defined as G mu is R mu minus 1/2 R G mu. So I define it. And what does Bianchi identity in this form tell us about the Einstein tensor? Exactly. So the Bianchi identity tells us that nabla mu G mu is nabla mu R mu minus 1/2 nabla mu of R G mu. This is just as Now Ricci tensor is symmetric, so the Einstein tensor must also be symmetric. G is symmetric, R is symmetric, so Einstein. Is symmetric.
So it's 10 under 10 independent components in the 4D space.
Maximum. With zeros. So it's not going to be a big surprise if I tell you that we are pretty much nearly there to get to what we need to do at Einstein equation. Let's say Einstein tensor. Questions about that? Let's see what it takes us to get to Einstein tensor. Right. It's far from being trivial. Okay, so now it's time to give a few examples to help you a little bit get your head above the water here. Okay, so I already said that last time. In one dimension, you have a one-dimensional space. It cannot be curved. It can look curved if you're looking at it from an n-dimensional, embedded in it. What you're seeing here is a one-dimensional space embedded in a two-dimensional space. Right? But from the point of view of somebody who lives in that one dimension, think of an ant lives here. It's a one-dimensional ant which lives in a one-dimensional space. It can only move either this direction. There is no notion of curvature. The metric is the same whichever direction she goes. Okay. Cannot cross that. Right? Just has to go through here. Two dimensions become more interesting. We said in two dimensions there is only one independent component, which means that everything we can know about the curvature of the space is given in the Ricci scale. Ricci scalar, to the one. Let's look, for example, the ceiling. What's the curvature of a ceiling there?
It's radius.
What?
It's radius.
It's what?
Radius.
Any other suggestion? Well, it's zero. It's not curved at all. Why? Is this paper curved? No, it's flat. No, I made a mistake. It's a cylinder. It's not curved. What is a cylinder? Is just a two-dimensional flat space which I identify the two boundaries, basically. What does it mean, practically? I can find a metric, don't have to, but I can find a metric which would be equivalent to the flat metric.
So if there is a map without any singularities from the flat space to your object, you can say that it's flat.
This is flat. If I'm going, now let's say that I'm a creature that lives here, right? A two-dimensional creature that lives in this two-dimensional space, which happens to be the torso. Can I tell that something is not flat here? No. And so I can say this is enclosed. So if I can go, I will go back to the same point it started. That's still flat.
Well, I'm not talking about the basis of the cylinder, right?
Yeah, I'm not talking about the basis. I'm just saying that I can find a metric in which this cylinder is flat. Same I can say for a bagel. What is a bagel? How do I make a bagel? Take a cylinder. Take a cylinder. Identify this space. I have to be a little bit careful here in what I do. It's actually it's a conformal flat. Exactly. I think there's a big mathematical subtlety here which you encounter at home. But yeah, it's basically it's got conformally flat because there is a metric in which is equivalent to a flat metric. That's by the way it's called S1 times S1. We're talking about a sphere. We took a two-dimensional sphere. Surface of the Earth. That's an example. Right? What will be the metric? B squared. A squared, delta squared plus some squared delta phi squared. Right? You've seen that. So again, I'm not going to do all the derivation because this is something that you're supposed to do at home. You already did that. Then we get the affine connection because anterior components gamma theta phi phi is minus sin theta gamma phi theta phi is gamma phi phi theta is equal to tan. Everything else is here. Which means from that we can calculate the Riemann tensor. One component of the Riemann tensor. For example, R theta phi. And it's enough because once I have it, the rest of the relations. So this is D theta gamma theta phi phi. Phi gamma theta phi plus gamma theta. I have a dummy index. Gamma phi minus gamma theta phi lambda gamma theta phi. This will be a dummy index. So d theta gamma theta phi phi. What is that? The over theta of that.
Minus cosine. Minus cosine.
It's going to be minus cosine squared plus sine squared. Sine squared theta minus cosine squared. Right? D phi, that 0. Gamma theta gives me 0. This one gives me a minus gamma theta phi lambda. So it has to be a phi. Right. So this would be a minus sine theta cosine theta, and phi theta phi is cotangent theta. Choose sine squared theta. Now we can lower the index. If we lower the index, what do we get? Oh, theta phi. G theta lambda or lambda. Which in our case the only one would be G theta R theta R theta. will get the 0. We put a phi here, g theta phi, that will give you 0.
Ah, yeah, okay, yeah.
Right. What is g theta theta?
1 raised to
A squared. A squared sine squared theta. It's not that difficult. Everything else, all the other components that we have here, either going to be related to that, either plus or minus because of the symmetry, or going to give you 0. Just check it out. What about the Ricci? So Ricci tensor. GR alpha beta R alpha mu. You end up that R theta theta is G phi phi R phi theta, which is what? What is G phi phi?
sine squared A squared.
1 over.
1
1 over. So 1 over A squared sine squared. What is R phi theta phi theta?
either
The
plus
same.
or minus of the same.
I switch once, I switch twice.
The same.
So it has to be the
squared
same,
sine
right? So the same. So what is R theta theta?
1.
1.
1. What is R theta phi? What is R phi theta? Oh, it's going to be 0. R phi phi is G theta theta. R phi phi is a what? Sine squared theta. What is the Ricci scalar? R is G theta theta. R theta theta plus G phi phi R. Do you get?
1 plus sine.
What is R? G theta theta?
Ah, it's
1 over x.
1 over A squared. What is G phi phi?
1 over a squared sine squared.
Times sine squared theta.
So in total is
So you get total
2 over a squared.
2 over A squared. This is a constant number. And to give you some intuition, if we go, A goes, if it's a sphere, well, first of all, it's a constant, right? And a constant gives you the idea of maximally symmetric space, which you can intuitively understand. It's a maximally symmetric space. It has a constant curvature everywhere. The larger the A is, what happens to the curvature?
Smaller than
It gets smaller and smaller, right? Actually, when A goes to infinity, we get up to flat. So you get some idea. Hopefully, you get some idea. Another thing here with the Ricci scalar, it's always positive. It's sphere. It's always positive.
Ah, a sphere, not over a
Sphere. Always on the sphere. Sphere. It's always a positive. Right? And the positiveness of the Ricci basically means that the space curves away from you in the same direction, in the same manner, same way in all directions. So if you're standing here somewhere, with the curve, it's always curved in all directions. In all directions, it curves the same way. And you can envision that if you had a negative curvature, that means that in different directions it would curve in opposite ways. So this is sort of subtle, a little bit difficult for me to draw. So if you're sitting somewhere here, saddle, this goes away in one way, this goes away in the opposite way. This will be a negative curvature. Okay. Questions? No? Fine, happy. Okay, so it's it's not that terrible. You just need to get used to it. As you work with that, it's like so constants.
Is there any meaning of this 2 in the numerator, which is kind of
It's a constant, the scalar. The meaning here is that it's constant everywhere. Constant everywhere really means that it's the same curvature everywhere, so that's what is maximum is space.
but sometimes
3D space equals 3, or it's not how it works.
No, it's not. 3D space you have more than one. That, of course, the Ricci scalar will depend on the place that where you are. Right. I'm not familiar with any meaning. It's more a matter of normalization. You could redefine the metric. Redefine A to be A over square root of 2 of that. That's allowed. If you have, for example, a American football ellipsoid, and it's not a maximizing ellipsoid, that means that you still have one number that is 2 dimension, but then it will depend on the place you are. It will not be a constant, it will depend on the location you are on this surface. Okay? So there is one last thing I want to do, which is related to the curvature. I don't even have to do it, I just think it's fun. And it sort of closes a loop. Now that we have discussed that. So it's slightly mathematical, but I think it's worth spending like 10 minutes just doing the derivation, sort of just to close the loop on something that you discussed. And that's called the geodesic deviation. So, what we're going to do next basically is to derive Einstein's equation. Right? But I said that the curvature, which is a use of the curvature to, I said, right, that the basic question that we ask is how the existence of matter acts to curve space-time. First, we said we need to know what it means to curve space-time. But before we're actually going to do that, let's look at the curvature, how it is manifested in a physical problem. There was one physical problem which we already discussed, if you remember. We had this question of what happens when people in the elevator are freely falling. Right? Remember that the whole starting point of this whole discussion and all this math was, okay, can we measure gravity if we're in a freely falling system? Had gravity, and there was an elevator, which was free falling. It contained 2 physicists, which tried to measure gravity, tried to even know that they are free falling in the presence of gravitational field. And we said that to first order there is no way they can do that, because gravity cancels out. It's a weak equivalence principle. But then we said that actually they do have a way of knowing. Measuring. What was that?
Changing out.
they become closer to each other.
In there?
Become closer to each
They
other.
become closer, right? Because the gravitational field that they feel is not exactly uniform, but both of them feel that they are attracted to the same point, the center of the Earth, and so if they do nothing, they will just see themselves slowly getting closer to each other. Then they can deduce that there is some gravitational field. This is, of course, a very small fact. It's a second order, but it's there. Right? But this is only because the gravitational field is not constant. It's not uniform. it's slightly changing from one point to the other. Now we can actually calculate it, because now we have the tool to calculate it. So, and calculating how we have two particles, two trajectories, and moving the influence of the gravitational field. So there is slight deviation from being parallel, right? Those objects move along geodesics, right? But the geodesics are not exactly parallel to each other, but there is a slight difference. This slight difference is something which we can actually now calculate. How it is. I guess you can guess what the outcome is going to be depending on, of course, on the let's derive it. Yes. What?
The distance
On what?
the distance here.
I'm talking general. What about two geodesics in arbitrary gravitational fields? So I have two trajectories.
Which is
So consider two trajectories of freely falling particles. So the two trajectories will be denoted by x mu of tau and x mu of tau plus delta x mu. They are pretty small. Deviation from each other. Equation of motion. Equations of motion. Given geodesic. So we have e squared x mu tau squared plus gamma mu rho sigma dx rho over the tau dx sigma over the tau is equal to 0. That's for the first particle. For the first particle, second particle, e squared x mu plus delta x mu the tau squared plus gamma mu rho sigma. You should say evaluated at x, you evaluated at x plus delta x. V x rho plus delta x tau. D x sigma plus delta x sigma over tau is equal to 0. So of course we take the differences, take 2 1, 2 minus 1. We end up that this is v squared delta x mu over v squared. Now I have to take a difference here, so this would be plus, first that terms first, so readings d gamma mu rho sigma over dx alpha, delta x alpha. dx rho over the tau, dx sigma over the tau. Now the difference is here, so I can, I only take, since delta x is small, I only take the first order correction, second order goes to 0. So the first will be just, and since I have one is dx rho and one is dx sigma, and they are symmetric, so I can simply write this 2, so I have a 2 times gamma mu rho sigma dx rho over the tau d delta x sigma tau, and all that is equal to 0. What? Well, again, I have here 3 delta x's, right? So the first one I just take the delta x, difference between that. I take that at x, because this correction will be small. Then I take one of these, so the rest I keep constant. So if I keep constant, then the difference will be just d delta x sigma over the tau. So essentially I have the same with d delta x rho over the tau times dx sigma over the tau. But because of the symmetry of gamma,
Okay.
then I can simply, they're both equal, so I can just write that as it. Okay. Now that really means a lot. We can use this result to write the acceleration, the relative acceleration of two bodies. So the relative acceleration of the two bodies, A mu is d squared delta x mu over tau squared. So relative acceleration. This is equal to d over tau of d. That's a covariant derivative. So it's d delta x mu over tau plus gamma mu rho sigma dx rho over tau delta x sigma. This is just a definition of the covariant derivative. I still have another covariant derivative, so that makes one as well. So this is d squared delta x mu over tau squared plus d over the tau of that part gamma mu rho sigma dx rho over the tau delta x sigma. Now I have this extra gamma because of this covariant derivative here. So plus gamma mu with alpha beta dx beta over tau of v delta x alpha over tau plus gamma alpha rho sigma dx rho over tau delta x sigma. Okay, I have this extra term that comes from the covariant derivative here. And this is because I have to take the regular derivative of that term here. So I take this all together, and I have a mu, the relative acceleration, is d squared delta x mu over d tau squared plus, again, because of the symmetry here, so here, that is there, yes, but I have the symmetry here, so I have plus 2 gamma mu rho sigma dx rho over the tau d delta x sigma tau plus d gamma mu rho sigma over dx delta dx delta over the tau. That is the derivative with respect to tau of this gamma. Dx rho over the tau delta x sigma plus the last two terms, so this will be plus gamma mu rho sigma d squared x rho tau squared delta x sigma plus gamma mu alpha beta gamma alpha rho sigma dx beta annoying, but straightforward. But now I can use that relation in here. I already have this d squared, so I end up with an a mu, which is the two gammas would cancel out. So I have what is left here. D gamma mu rho sigma over dx delta. Dx delta over tau. Dx rho over tau. Delta x sigma. Then I have the minus term from here. Minus d gamma mu rho sigma over dx alpha delta x alpha dx rho over the tau dx over the tau, and then whatever is left, which is the last two terms here, so plus gamma mu rho sigma d squared x rho over d tau squared delta x sigma plus gamma mu alpha beta gamma alpha rho sigma dx beta over the tau dx rho over the tau delta x sigma. Have to do this thing slowly. Make sure that you practice all of the indices. There's nothing to it, just open it. Now, use the geodesic equation. D squared x rho over tau squared is minus gamma over sigma nu. Sigma over tau, dx u over the tau. And then we start to play with the indices. So what we really do here is now there is a small term which will be sigma here next to alpha. And delta goes to sigma. Sigma. Here we have rho goes to lambda, and sigma goes to alpha, and usually alpha goes to lambda. Sigma goes to alpha, beta goes to sigma. The next one, which I'm not sure where it is, we end up writing this equation in the form A mu is d gamma mu rho alpha over sigma minus d gamma mu rho sigma over dx alpha plus gamma mu sigma lambda gamma lambda rho alpha minus gamma mu alpha lambda gamma lambda rho sigma times dx sigma over tau dx rho over the tau delta x alpha. What is that? It's in the ring. So we end up A mu, which is d squared delta x d tau squared. Use R mu rho sigma alpha this is called the geodesic deviation equation. Again, what does it tell us? Same thing. I mean, the intuition here is very simple. If I am an astronaut, whatever, I'm flying along the geodesic, and you are an astronaut nearby, you're flying also along the geodesic. But because the gravitational field that we both feel is not uniform, there is some curvature in the gravitational field. Then I'm going to see you accelerating with respect to me. Acceleration depends on the distance between us, or delta x, and curvature delta. It's quite cool. That basically answers the problems closest by a star a few weeks ago. Questions about that?
If the distance larger, the rate of
Again, right? When I did here, I did during the calculation, I assumed it's a small
okay.
deviation, right? So then we start having higher order terms, and it starts. Right? So this is first order in the Taylor expansion of this.
it doesn't necessarily that if we space in space-time, the distance between us is larger, the acceleration will be higher.
Again, this is for two nearby, two particles on nearby trajectories. If you go too far, then it gets cannot use these approximations that it's doing here. Okay. So don't get into the point. That's just to show you that basically I closed the loop. I told you we discussed two scientists in a free falling elevator could determine the gravitational field by looking at the acceleration of one relative to the other, and that's the exact mathematical expression. Okay. Any further questions? Nope. So finally, we're reaching the heart of this course. After spending a few weeks and a lot of math, we have all the tools needed to answer the question that we put in the first lecture. Einstein's good for you. Now we're going to switch to physics. Question we have is, how does matter energy acts to curve space time? Obviously, there is more than one way to look at this equation. What we're going to do here is something which is closely following the path that Einstein himself took. That you can find in textbooks. There are at least 3 ways of deriving that equation. But this is the most, in my opinion, this is the most straightforward way, or most intuitive way of deriving this equation. And the starting point is Newton. How do you write down the Newtonian equation? more precise. Poissonian equation describing Newtonian gravity.
CR to 5 is equal to the density of mass.
Poisson equation. Poisson equation. Now let's go to phi is 4 pi g. Nabla squared phi, Nabla squared. Ij, ei, dt. What is rho? This is a mass density. Look unhappy. Yeah, you know, we're familiar with phi minus g over r. What does it mean? Where does it come from? This is a solution to this equation for a delta function of rho at r equal to 0. We don't care about r equal to 0, we want to get a type of general expression. So we want to generalize that. What do we have here? Quickly general discussion. What do we have here?
Second derivative of potential.
Second derivative of
Maybe
potential.
the second derivative of the metric.
That's right.
Riemann tensor. Something.
This is a second derivative of the potential. What do we have here?
Source.
Distribution of masses. So the mass distribution. That's one thing. Second thing, what type of equation do we look for? Tensorial. Equation we look for should have tensorial. So what's the tensorial generalization of that part? That is easy. Certainly, this is obvious. So this should be. What do we have here? That's the main question.
Has to be Einstein then.
It has to be eventually, yes, but that's in the Newtonian limit. Right. Remember the Newtonian limit has T mu nu T00 is equal to rho, and G00 is minus 1 plus 2 phi. Remember we derived it. So in this limit, we have Nabla squared. H00 is minus 8 pi G where H00 is 2 phi minus 2 phi. Those things we had. Now we want to have the full generalization. This is not easily generalized to tensor. Because if instead of Nabla squared we go to D'Alembertian, this is Nabla nu. Can we do that?
Was in common.
What?
Common.
Sorry?
Was in the common.
No, that's fine. But can I generalize Laplace squared? Now, okay. Now I try to generalize this equation. So I know that this equation is correct in the weak field limit. Right? We already showed that a few few weeks ago. Right? Question is, can I generalize that? So the first choice might be to use the Dalibert. Yeah.
Ah,
Can I do that?
no.
No. Why? Why can I do that? There is a covariant. What's the problem? Why cannot use the Dalibert? Zero, right? Why? It's called the metric compatibility. Right? So I cannot simply use that. So it's, I cannot put here G. Like in the left hand side. What can I put here? Instead of Laplace squared H. You understand the question?
Yes. What generalize?
I want to generalize this equation. Okay. So Laplace squared of G, I cannot put here G, because if I do, I get a zero automatically. What should I put here? So I need the second derivative, something which is related to the second derivative of the metric. Tensor. So it's a Riemann tensor. Can I put the Riemann tensor?
No.
No. Why not?
It's 3, 1.
It's a 1-3. It's a 1-3 tensor, and here I have a 0-2 tensor. So Riemann tensor is not going to work because it doesn't have the right number of indexes. Right? Ricci tensor. Now we're talking. So we can think of an equation of the form. So we can try. The Ricci tensor equation of the form R mu nil is some constant kappa T mu. That looks quite reasonable. First try. In fact, history textbook says that this I should actually try. And we'll explain with these equations. This is an option, but this option is not working. Why it is not working? Well, let's see. But what's the problem? And kappa, of course, is a constant. We can determine potential. But what? Conservation of energy. Energy momentum. How do we write down conservation of energy momentum? What is the if I tell you conservation of energy and momentum? What is conservation of energy and momentum?
There is a curve associated.
What's it? If I tell you write down conservation of energy momentum equation.
Stress energy density.
Nabla mu T mu is equal to 0. This is conservation of energy momentum. That means that we should get from here that nabla mu of R mu nu is equal to 0. This was the right equation.
Correct.
Exactly. But that's not always true. Because by Bianchi identity, we have nabla mu is 1/2 R. This R, this R, we should write it as, you can just multiply it by G, by inverse G, right? So I get R is equal to kappa G mu mu T mu. So it's kappa T, right? T is the trace of the special stage of means that if I believe that, that means that nabla mu of t is equal to 0. Is equal to 0. Which means what? This is a covariant derivative, this is a scalar, this is just a partial derivative. So that means that t is constant. So that means that t constant. That doesn't make sense because in vacuum t would be 0, but inside the star or something it's not. So but t is equal to 0 in vacuum. T greater than 0 in matter. So no go. So what will be the next choice for the Riemann? So this is Einstein. So the next choice will be Einstein. Try, so second attempt. Let's try the Einstein tensor. G mu nu is R mu nu minus 1/2 R G mu. What about the nabla mu G mu nu? 0, 0, 0. That's a Bianchi identity, right? What does it mean? Why do you say it's 0? So the Bianchi identity was not just an identity. It has a physical meaning, quite strong physical meaning, which represents conservation of energy. That's why I said we're getting to the point here, right? Because, that's the really ingenuity of this. Take something which is pretty mathematical, with a real physical meaning. This is equal to 0. So let's try right here. G mu nu. G mu nu is equal to kappa T. Okay. So the question is whether this equation, so it has basically everything we want. The question is whether this reproduces back the Poissonian equation. This equation. This is what we need to show. So let's do the contraction. G mu nu, G mu nu, G mu nu, R mu nu is 1/2 R. Yeah. G mu nu times R. Union? Just R. It's R, which is scalar, right? We have here minus 1/2 R G mu nu is equal to kappa T. This is G mu nu, yeah. 4. 4, read everybody. This is 4.
Not 3.
No. 4. Space time. Think of G mu nu in
Minus 1, 1,
minus 1, 1 on 1. So multiply that together. In flat space time, of course, but this is the zero equation, so it's true. It's always true. Right. So we have R. So R minus 2R is a minus R, so R is minus K kappa T. So we can write that. Use that here, and we can write that as R mu nu is equal to kappa T mu nu minus 1/2 T G mu. Here's a trace of the stress energy tensor. Now I argue that this gives the correct prediction for the Hamiltonian equation, Hamiltonian equation. So, in the Wakefield limit, remember all the conditions we set. Velocity is much more than c. Only the t00 is important, and then time independent, so the particles, etc. So we got that rho is equal to t00. It's going to be much greater than all other t mu mu mu. So neglect them. Then we have g mu nu, it's eta mu nu plus h mu nu, where h mu nu absolute value is smaller than g mu nu. That's right, it's 1 and 1. Of course. And inverse g mu nu is eta minus h mu nu, simply by Taylor. So overall, we have that the g00 is what? It's minus 1 plus h00. G inverse is minus 1 minus h0. The trace of the stress energy tensor T is a what? Just have to suffer. Right? So it's just g00. T00 because all the other terms are much smaller. That is a minus T00. Yeah. If I take all that, put it here, bring that over here, end up that R00 this is just T00, T00. This is a minus, minus, it cancels out. So overall I get, sorry, this is a minus T00. This is G, it's a minus 1, so they cancel out. T00 minus half T00, so just 1 half. So just 1 half kappa T00. Maybe I can. So end up R00 is minus 1 half plus 1 half kappa T00. That's R00. Now, actually, what's R00? R00 minus R lambda 0 lambda 0. Now, R with all zeros, what is it? If you follow what I said, you should know the answer right. What happens when I change two indices? Minus. So what it should be? 0, 0. Thank you, right? If I change that, right? I change it to J, but it's 0. Minus. It has to be 0. Right? This has to be 0. So what I care about is only RII here. R I0 J0 is by definition dj gamma I00 minus d0 gamma I J0 plus gamma I J lambda gamma 00 minus gamma I0 lambda gamma lambda J0. This is a time derivative. The static metric, there's 0. These contain gamma square terms, which are small, so I don't care if they're small. first order, just have Ri0J0 is equal to Bj gamma 0, 0. So, yes. So we have it R00 is Ri0, I0. So I just have to know that that's a Di 1 half G I lambda D0 G lambda 0 plus D. We're late, but we started everything. Plus D0 G 0 lambda minus D lambda G 0, 0. Which is just minus 1 half. So D0 we said we don't care. So the minus 1 half eta j di dj and g0, 0 between a0, 0 plus constant. This is minus 1 half lambda squared a0, 0. This is r0, 0. Z is equal to half kappa 0, 0. So if we compare that to what we have here, we get that lambda squared a0, 0 is equal minus kappa t0, 0. From here, we just say that kappa is equal to 8 pi g. So with that, we just plug the things in. And we get that G mu nu, which is R mu nu, minus 1 half R G mu nu is equal to 8 pi G T mu nu. That is the generalization of Poisson's equation to any arbitrary gravitational field. This is known as Einstein's equation. One thing before we leave. See, we lost one. What is this? This is physical term. This tells us the distribution of matter in space. What is this? It's a geometrical term. This tells us how the space-time is being curved. So this is the real ingenuity. Einstein took physical quantity, T mu nu, and associated with that curvature, which is what we want. This is how matter acts to curve space-time. I'm already quite late, but I thought it was worse not stopping that in the middle. This where we stop, and then we of course continue to discuss that equation and its consequences for the rest of this course. We'll do a little bit more statistics because we need to, and then most of what we do from here on, at the end of the semester, we look for solutions. So from here on, things are going to switch direction, getting more physics than math. Questions?